So our second speaker of the evening is Professor Karen Seto, the Frederick C. Hickson Professor of Geography and Urbanization Science in the School of Forestry and Environmental Studies at Yale University. Professor Seto has played a leadership role in the urban mitigation subgroup of the Intergovernmental Panel on Climate Change, or the IPCC, and was a member of the U.S. National Research Council Committee on Pathways to Urban Sustainability. She's a fellow of the American Association for the Advancement of Science, a Leopold Leadership Fellow, and a member of the U.S. National Academy of Sciences. Professor Seto will speak to us tonight about global trends in urbanization and the attendant risks that result from the extreme events that are characteristic of a changing climate. The title of her presentation is Hotter, Wetter, Drier, Global Trends in Urbanization and Challenges for Climate Resilience. Please join me in welcoming Professor Seto to the stage.
Okay, wonderful. Well, thank you for the invitation to come speak at this symposium. It's really an honor to be here. When I thought about what I wanted to speak about today, as a geographer speaking to, I'm assuming, primarily engineers, I was thinking, what insights could I offer to folks who actually design and build the built environment? And I thought probably the biggest take-home message I could provide is that which a geographer would, which is that we need to think about resilience at a very different scale. So the take-home message of my talk today is we need to think about urban resilience in a very different scale, both temporally and also spatially. And I'm going to start off with a tale of 3 different cities. And I should start off by also saying that I am not an archaeologist, and much of what I've learned about archaeology comes from my colleague Harvey Weiss, who is an archaeologist. So I'm going to start off in Greece, take us to Mycenae in Greece. So Mycenae was a town that actually eventually became many towns. Was essentially kind of like an empire, and the Mycenaeans were very good builders. They were like very good engineers. And what's interesting is if you look at the archaeological record from archaeology, there had been many stories that had been written that basically suggested that the demise of this civilization occurred because of climate. But maybe perhaps because these stories were written in the archaeology literature and not with lots of data, lots of graphs, they were basically taken as anecdotes. So this empire basically stretched out across the Mediterranean, and as I said, they were really good builders. But what's interesting is over the last 10, 20-ish years, with advances in paleoclimatology, so this is basically taking data from caves, from pollen, ice cores, tree cores. Scientists, climate scientists working alongside with archaeologists have now basically told the same story that archaeologists have been telling for a while. That perhaps, well, more than perhaps, there's a very strong evidence, data-driven information that shows that there was a big drought that happened. So these are data that show on the very top, this is paleo rainfall. The second line shows pollen count, which is another indicator of rainfall. And the bottom 2 rows basically show the occupation of different sites around this region. I just want to highlight 2 different areas in this graph that show that basically the paleoclimate shows that there was a decline in rainfall, and that this decline in rainfall happened not only just over a course of 1 year or 2 years, but actually it happened over decades and centuries. And synchronous with this change in rainfall was the abandonment of these cities and towns. So that's Mycenae in Greece. Let's move to the Americas, so Chichen Itza. Again, there had been a number of stories and articles, studies in the archaeological record that basically suggested that the demise of the classic Mayan civilization occurred in conjunction with changes in climate. But again, like Mycenae, a lot of those archaeological studies were taken as just, well, they're just anecdotal studies, not enough studies, not enough data. So again, paleoclimatologists working alongside archaeologists now have shown that, in fact, the Yucatan Peninsula faced a number of, not droughts in this case, they actually call these flip-flops, significant climate flip-flops that lasted over hundreds of years. And in fact, in this article that was published in Science, the authors of the article write, droughts occurring during the disintegration of the Mayan civilization represented up to a 40% reduction, just a 40% reduction in annual precipitation. And if you look at the graph here, what you see is there was quite a bit of flip-flopping during this period. The other thing about the Chichen Itza and the Mayans is that they called it a modest drought. It wasn't a severe drought, it was actually modest. So the same story actually goes with the Roman Empire, also plagued with climate flips. And here it's even much more severe. You see a lot of, over a 10-year period, 20-year period, you see that it went from very hot and wet to very dry and cold. And this back and forth, basically the climate record is suggesting that this wide variability in climate led to the inability to farm, led to the disintegration of economic and political institutions. Essentially, if you think about this from a farming perspective, if you can't predict what the rainfall, what the temperature is going to be next year or next century or next decade, that actually has a very destabilizing effect. And that's basically one argument for some of the why we had the fall of the Roman Empire. So here's Harvey Weiss's book on the right. He and a number of colleagues put together 9 case studies from around the world. But there are more than 9 case studies. And I think one of the take-home messages I get from Harvey's research and others is that we need to think about climate impacts on cities at a much, much larger scale, both in terms of the time horizon, but also in terms of the geographic region which is actually affected by climate change. So let's move to maybe the more near present, and let's take a look at what the Earth's surface temperature looks like over the last 100+ years. So here's some data that shows surface temperature over the last 140 years, and I think most of us in this room are familiar with these data that show that essentially the temperatures continue to increase. And if we look at this over a longer period, so this is over the past 1,000 years, we see that what's happened since the Industrial Revolution is really significantly different than over the longer period. So we are clearly in this era, this period, this temporal period where it's unlike anything that we've seen before, at least in the last 1,000 years. How will we actually prepare for these radical shifts in temperature, in precipitation, not just in the cities, but all around the world? The previous speaker spoke to this a little bit about extremes. Climate change is not just about increasing temperature, it's actually about changing the extremes and the magnitude of these events. So what we're seeing around the world is much more extreme events, whether it's more extreme precipitation or very, very hot days, or not just even hot days, but very hot spells, very cold spells over a long period of time. And so we're seeing all around the world that we see increases in hot days and warm days, but they're also lasting for a longer period. Same thing with more precipitation. So some places we're getting more precipitation, but over a longer period as well. So we need to think about not just shifts in climate and temperature, but also the occurrences of these extremes. So this is a graph that's taken from the most recent IPCC report that I think is useful in helping us think about shifts in climate. That essentially we're talking about 3 different changes. On the one hand, we're talking about a change in the mean, the averages vary. So it's not just as easy as going to the Farmer's Almanac and saying, what was the temperature like here last year or 2 years ago? So the mean value is actually shifting. But the other thing that's shifting, and which is shown in the second graph, is that we have a lot more variability. So one of the challenges with having a lot more variability is that it becomes harder to predict what we're going to do, whether we're a farmer or whether we're a planner or presumably whether we're an engineer. And then the third graph shows this changing shape, that essentially it's not just that there's more variability, it's that summer used to come between June and August, but now maybe summer's coming during a different period. And there's some really interesting research that just came out this past week that is basically showing that around the world there's this mismatch in phenology that's happening. That spring is coming up earlier in the year for many parts of the world, and that many species cannot keep up with that. So what happens when plants start, they're blooming earlier in the year, but what if their pollinators aren't catching up or on that same schedule? So these are really big phenology mismatches that result from this changing shape, that essentially it could be that we have a snowstorm in the middle of summer. We actually did have a snowstorm, I think it was 2 years ago in New Haven on Halloween, completely disrupted trick-or-treating. Now, that was just a minor nuisance for the kids who were getting ready to go out, and we had trick-or-treat the next day. But could you imagine if we actually didn't have the regularity, we didn't have the predictability? I mean, that's what scientists, that's what we do. It's all about being able to replicate and predict what's going to happen in the future or in these other places where we haven't been before. But climate change is putting that on its head because we may not be able to predict when the seasons occur, when we're going to have rainfall, when we're going to have droughts. So another couple of slides from the IPCC. This one shows on the left the changes in consecutive dry days, and on the right, this is soil moisture anomalies. So essentially, this is just giving us a sense of dryness in using 2 different types of models, 2 different types of data and models going into the future. I want to ask folks, raise your hand if you went directly to Montreal on these maps. Come on, you're an anomaly then. Because most people immediately go on the map, go to the map area where they are living. And I would argue that climate change resilience for cities means that we have to not only look at where we're living, but we actually have to look worldwide because most of the resources that support our cities don't come from our cities. So we probably have to look at Alberta and maybe the region of Alberta and think, oh, are energy resources actually resilient? In the US, we would probably not look I would not look just at New Haven, but I might look at Iowa, and I would think, is our agriculture resilient? I might actually look not just in the US, but I actually might look at China, and I might think, okay, Are our transportation infrastructure in China resilient to these kinds of massive changes that are underway? So this is one of the main take-home messages that I want to leave you with. I'm not done yet, though. But I do want to say, I do want us to think about urban climate resilience, not just in terms of one city and our city where we live, but how can we think about a resilient system? So another data set, this is from another data set from the IPCC, which is showing changes in average surface temperature in the top graph, and on the bottom graph, this is changes in average precipitation going into the future. And again, if you take the systems perspective and a planetary perspective, and not just your local city, it's very easy to see that many different regions around the world are going to be stressed by climate change. They're going to be stressed by increases in temperature, wild fluctuations in precipitation. And so when we start thinking about the resilience of a city, we have to think about the supply chains, and we have to think about the resilience of these very different ecosystems and not just the urban one. Often, when I talk to policymakers, especially right after the IPCC report came out, the authors were sent to many places to speak with policymakers about the report. And one thing that came up a lot in the context of the urban chapter was policymakers wanted to know how could we be resilient, more resilient to these extreme events that might happen once or twice a year. Maybe the 100-year flood happens more frequently, as we'll hear about later, I think. But I think the image that many folks have is, how can we be more resilient now for an event that might happen once or twice? And so this image, this picture of the melting tarmac in India that just recently happened, I think is kind of indicative of that thinking of, well, how can we actually make the tarmac better? But I would argue, actually, that's not the system's way of thinking about this, because it's not just the tarmac, it's that if temperatures, let's say, exceed 50 degrees C over 2 months, who's going to work outside? How are we going to get from places of origin to places of destination? Having a hybrid car is great, and having low carbon buildings is terrific. It all has to be part of the package. It has to be part of the solutions, but we also have to think about how do we redesign and rezone cities so that we can be more co-located between places of origin and destination, so that if we do face a future where we have 50 degree C days over many, many, many days, how will our kids play outside? Where are other places for them to play? What do we think about mobility and transport infrastructure? How do we think about basic things like taking care of all the infrastructure that's already in place? Because who's actually going to be outside? Something else to think about. So it's beyond just the tarmac. And that's what I want us to think about. To think about this much more in a systems perspective. So these are pictures and images that I think a lot of people have when they think about resilient cities. They think, well, how do we build our road infrastructure to be much more resilient against storms and flash floods? How can we deal with flooding? And how do we, we're going to hear all about that, so I won't talk any more about it, but a lot of questions about how do we deal with these extreme events that the vision often is it might happen over a short period, or it might happen just once or twice. But again, I would argue that we have to think about this in a much, much more systemic systems perspective. So I only have 3 take-home points for this talk. And the first one is we're facing a hotter, wetter, drier world with more extremes. And a big question for us, I think, as a science community, but certainly as a practitioner community, is how do we actually rethink urban resilience? How do we rethink how cities can be resilient to climate change, given that most cities around the world get their resources from around the world? And if there's anything that we can learn from the tale of those 3 cities, how can we incorporate ideas, forecasts around multi-decadal or maybe century-long climate events What does climate resilience look like in those terms? I'm going to show this little video, which was made 18 years ago. 18 years ago, I was on a NASA panel at the AAAS conference in the US, and the panel was basically a bunch of NASA scientists. We all were using satellite data to map and monitor the growth of cities and how the growth of cities shapes their climate. And NASA wanted a lot of people to come to this conference or that particular panel, so instead of calling it something scientific like urban growth and climate, the title of that panel was Weird Weather. And we had a packed room of a lot of journalists because it was, this is 18 years ago. I think many of you in the room were wee big then. But when I look back at that panel, I'm actually, sad is not the right word, but disappointed that we as a scientific community haven't embraced the terms weird weather. Because in many ways, that's what climate change going into the future will look like. It's not just about global warming, because the data shows that it's not just increases in temperature. Some places are actually getting drier, some places are getting a lot wetter. It's actually that we're not going to be able to predict what might happen in the future. And so we're going to have a lot more of this, quote, weird weather. What this video is going to show, and remember, it's 18 years old, before Google Earth, and this was all using NASA satellites, with the exception of one satellite, which was a NOAA satellite. What we're going to see is it's going to zoom into Atlanta, Georgia, in the south, in the US. And we're going to see some satellite data that show the growth of Atlanta over about a 30-year period. And so you'll see the growth of Atlanta, it's shown in red. And what the movie, I'm going to give you a preview because I don't want to talk during the movie. After we see Atlanta growing, the video is going to zoom out, and we're going to see a LiDAR image of the region. So this is a sensor that's flown on an aircraft. It's going to look like a band. And what it's going to show is Atlanta during the day and Atlanta during the night. And the thing to remember when you see that part of the video is everything that's white is hot, 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 hot. So the places that are the hottest are the top of buildings, parking lots, those are very hot. We're going to see Atlanta during the day, and then it's going to shift to Atlanta at night. And you'll see that Atlanta's really, really hot at night compared to its surrounding region. So that's the urban heat island effect, well established now. But to me, the most exciting part of the video comes at the very end. At the very end, we zoom out beyond Atlanta, and we see greater Atlanta, and we see a different GOES image, which is basically a weather satellite. And what you see is the development of cumulonimbus clouds. And you see the development of very severe storm clouds, basically. And areas that are red are these severe storms. And this is work that was done by Del Quattrochi and his group at Marshall Space Flight Center. And I wanted to show it because we know the urban heat island, it's well established, but there's growing scientific evidence that shows that cities are modifying their climate also in terms of precipitation and also in terms of extreme storm events. So we've got climate change to think about, which is happening globally because of CO2 emissions, but cities are also modifying their regional climate. So let's go through this. Let's see if this video works. I've just explained to you the entire video. Okay, here we go. I've reversed it in my mind. This is the LiDAR image. So areas that are white are really, really hot, and areas that are red are also very, very hot. So you see Atlanta's very hot during the day, but Atlanta's very hot at night as well. especially compared to the surrounding areas. So now if we zoom out and we see Atlanta and its suburbs over the 70s and 80s, 90s, you can see a lot of, well, you can't see it in this image, but a lot of this is actually low density urban development. And this is the GOES image, where you see the development of these storm clouds east of the city. And to me, this is a really powerful analysis that Dale's group did. Because again, this is 18 years ago, showing that cities modify their climate primarily by the types of materials that are used in cities, but also very much based on, also driven by the land use and land cover patterns within cities. So what's happening worldwide? I'm going to zoom out a little bit, out of Atlanta, out of North America, and I want to give us a different lens to think about climate resilience. So we're now at, I think, about 4.1 billion urban people who live in urban areas globally. And the most recent UN estimate suggests that by 2050, we're going to have about 6.5 billion people living in urban areas. The pace of urban development is really extraordinary, especially when you think that in 1900, we had fewer than 1 billion people living in urban areas. So the pace of this urban development is really amazing. And if this is just the population data, if we actually convert this into another number that might resonate more with engineers and planners, that is, how much land are we actually going to need? So my group, that's part of what we do. We actually forecast the growth of cities worldwide. We forecast the amount of land that's going to be needed and where they're going to take place. And we've done a couple of studies on this, and we show that roughly we're going to see the growth of about 20,000 American football fields every day for about 40 years. I should have probably converted this to hockey fields before I came, hockey stadia, but, and that would have been a more impressive number probably. But the message here is that we've got to build these cities of tomorrow to house all these people. And here, I want to just say that I'm an optimist at the end of the day. And that's why I was excited to come and speak at this symposia, because we have this window of opportunity to work together as geographers and engineers and economists, because these cities have to be built. And they don't have the lock-in that our established cities do. And at the same time, they can learn so much from the cities that have already been developed and are in the process, many of them, of being retrofitted. So what's happening around the world? We've got places like this. This is Shanghai in the late 1970s that today look like this. And of course, not every place is developing at the same pace of Shanghai. But now I've been working in India for about 10 years. I've been now working in the Himalaya. I've worked in other parts of Southeast Asia. And this kind of rapid development is actually not exceptional. Maybe having the Bund is exceptional, and maybe having really tall high-rise is exceptional. But the pace of development and the scale of development is not exceptional. And here again, I think this is an incredible window of opportunity for researchers and practitioners to come together to think, how do we actually design and build the cities of tomorrow? But there are a couple of major trends globally, major urban trends globally, that people don't talk very much about, that will have a significant impact on climate change going into the future and how we may or may not be resilient. And I want to highlight just a couple of these different trends. So one trend is household size. So around the world, this is happening in North America, it's happening in Europe, it's happening in Asia. Around the world, what's happening is household size is declining. So what that means is we have fewer people in a house or an apartment. And so this does not take advanced math right? So if we have an increasing urban population, but household size is declining, we're going to need a lot more homes. We're going to need a lot more space to house all these people, given that household size is declining. Now, there are some places, like in New York City, I don't know if this is happening in Montreal, but there are some places where there's a movement towards these mini homes. I don't know how sustainable that is. That may be a fad, that may be just a blip. Certainly, that is a trend that is happening, but the dominant trend is that the household sizes are declining. And the other dominant trend is not the mini homes, but rather the homes themselves are getting bigger. So in the US, we see that the home sizes, the average square footage of a home has significantly increased over the last 50 years. And again, this is not just happening in the US. We see the same data in China, in Vietnam, in India, very similar trend where household sizes are declining, but also the size of housing is actually increasing. This is some data that we collected for the IPCC, where we basically found that urban population densities are declining all around the world, across all income levels, across all geographies. And so this is a really big trend, and this is perhaps going to have a big impact on how cities modify their own climate. Because if you think about Atlanta was shaping its climate largely because of its land use pattern. And so if what we're seeing is declining densities and much more impervious surface, that's going to have a significant impact on things like hydrology, surface albedo, surface energy balance. So that's going to have this much more local impact. And at the same time, more houses, bigger homes, means that we have a greater reliance on resources to build these homes. And these resources often come from far away and often in places that are also going to be impacted by climate change. So again, this is just another way to think about climate resilience, urban climate resilience, in a much more systems perspective. The other trend, so I've just talked about the household trend, household size and home size. The other trend that's happening worldwide is cities taking place or growing over farmland. And so this is a picture taken from China, and we have examples from, again, all around the world where urbanization is taking place on prime farmland. And so my group, we've done a lot of analysis on this. We've forecasted future urban growth and looked at what are the farmlands that are most likely to be impacted. And the story is not very good for a few places and for four major crops. For soybeans, for maize, for rice, and for wheat, these four crops will be heavily threatened by urban expansion. We're going to have especially acute crop loss in Asia and also in Africa. I just want to highlight here, it's the, I don't know if I could have a pointer, but it's the second column from the right, which shows the production lost as a percentage of total crop production in those continents. So what you see in Asia is roughly a 5.5% loss in cropland. In Africa, about a 9% loss in cropland. And if you look at specific countries, like in Nigeria, in Vietnam, in Egypt, and a number of others, the percent loss of cropland due to urbanization is really significant. So we've got this trend where urbanization is taking place over croplands. At the same time, around the world, we see this really big shift in diet. So part of what we're doing in my group is also looking at how urbanization is reshaping diets. How is diet shifting due to urbanization? And what we're seeing is, in some countries, a shift towards much more processed foods. In the popular literature, you hear a lot about an urban meat-based diet. And I want to say that we have actually found that in some places, it's not just a move towards a meat-based diet, it's actually a move towards more food away from home. So a lot of cultures are not eating meat, and they don't have the money or the income to actually switch to a meat-based diet, but they are able to eat out away from home once or twice a week. And so that actually is shifting the production side and the supply side. In China, we do see a significant increase in meat consumption. There's another story behind this increase in meat consumption in China, which is that there's an increase in imported soybeans to China to feed cattle and pigs, and those soybeans come from Brazil. And so there's this very interesting link where you've got deforestation, which is reducing it's the lungs of the world, right, the forest, which is now used for soybeans, shipped over to China, used to feed cows and pigs. And this is all, again, related to these changes in urbanization, changes in urban income. So what we're seeing, my second take-home point, is changes in food demand, significant increases in the demand for raw materials, and at the same time, reduction in cropland around the world. So I think a big question for us as a research community is, how do we actually increase the resilience of ecosystems and the resources on which cities rely? So my last take-home point is really about the modern city. This is a video of the relatively new NASA VEER satellite, which is the Earth at Night lights data set. It's a data set that's probably one of the most recognizable NASA data set. What's phenomenal about that data set is it shows modern urban living, primarily urban living. So in my lab, we use that data, we analyze that data quite a bit. There are very few places in the world that are lit up at night that aren't urban. Now, the inverse is not true. There are many places in the world that are urban that are not lit up, especially in South Asia, especially in sub-Saharan Africa. But as spectacular as that image is of Earth at night and the night lights, big question around climate resilience in cities is power outages. We have had a number of power outages worldwide that have lasted a day, a few hours, and sometimes it's a nuisance. If you have to read at night, you have to have your shop at night, or you are stranded because the trains aren't running, that's a nuisance. But again, thinking back to the beginning of the talk and the tale of those three cities, if we think about power disruptions over a much longer period, over weeks, maybe months, or maybe years, and here I mean not just power disruption in terms of not having energy. It's not necessarily a binary issue. It's not just on or off, but it's also about the quality of the energy, and it's also about the reliability of the energy. And so I put here a picture of the Biosphere 2 project out in the West in the United States, and not to propose that that's what we should do, but it is a question as to how we think about powering our lives and our cities, because clearly modern cities would not be what they are if we didn't have power. And so I'm going to end with this picture I'm curious, has anyone been to this region of Turkey? It's very close to the Syrian border, Urfa and Haran. So these are homes that are designed to withstand very, very high temperatures. They're incredibly cool inside. They're incredibly low energy. They're built around a community. Clearly, we're not going to build this type of housing for 6 billion people. But I did want to end here and have us think about how we rethink urban resilience in a much more systemic, holistic way, where we link the resources on which cities depend with how we live, where we live, energy, and food. So this last message is really, how do we increase our energy resilience? in the face of growing vulnerability. So I think the question for us ultimately is, in this century of the city, is this urban resilience challenge, or is it really an opportunity, especially given how many cities we're going to have to build over the next 40 years? Thank you.